Howdy. I have been talking about scalability many times, and I have been talking about weather being totally electrical in nature. And that's why the high and low pressure systems spin the way they spin, positive and negative. But now let's go to phys.org. Ultra small swirling magnetic vortices detected on iron containing material. Microelectronics forms the foundation of much modern technology today, including smartphones, laptops, and even supercomputers. It is based on the ability to allow and stop the flow of electrons through a material. Spin electronics, or spintronics, is a spin-off. It is based on the spin of electrons and the fact that the electrons spin along with the electric charge creates a magnetic field. Forever spin. Huh. This property could be exploited for building blocks in future computer memory storage, brain-like and other novel computing systems, and high-efficiency microelectronics. Zed Jarduta Fadak, group leader in the Materials Science Division of the U.S. Department of Energy, Argonne National Laboratory. A team including researchers at Argonne and the National High Magnetic Field Laboratory discovered surprising properties in a magnetic material of iron, germanium, and tellurium. Telluricurrents. This just came to my mind. This material is in the form of a thin sheet that is only a few to 10 atoms in thickness. It is called 2D ferromagnet. Now listen. The team discovered that two kinds of magnetic fields can coexist in this ultra-thin material. Scientists call them mirrons and skyrmions. They are like miniature swirling storm systems dotting the flat landscape of the ferromagnet, but they differ in their size and swirling behavior. Known and studied for about 15 years, skyrmions are about 100 nanometers in size, approximately the same as a single virus molecule. And their magnetic fields flow in complicated patterns resembling those of the strands of a knot in a rope. Only recently discovered, mirrons are roughly the same size and have magnetic fields that swirl around like whirlpools. Yeah, like a galaxy. Resembling those of the strands of a knot in a rope. Yeah, galaxies form in strings amongst the cosmological Bertrand currents. But now we are at a really small scale. Both skyrmions and mirrons are very stable because, like firmly tied knots, they are difficult to untangle, says Louis Palicas, who holds a joint appointment at MagLab and Florida State University. This stability, along with their magnetic properties, makes them attractive as carriers of information. It's an electric universe. Energy is information. The team is the first to observe both of these magnetic textures in a thin film at the same time at low temperature from minus 280 to minus 150 degrees Fahrenheit. Also, mirrons remained present up to room temperature, an important consideration to exploit them in practical devices. In the past, they had only been observed at much lower temperatures in different materials. The team also showed that skyrmions and mirrons are detectable from their effect on an applied current by measuring the voltage. This feature means they are adaptable to the binary code used in all digital computers. Yeah, maybe the DNA looks like something like this. This code consists of combination combinations of 1 and 0 in a spintronic device, A1 would be indicated by an electrical signal detecting a skyrmion or meron. The absence of an electrical signal would then convey a 0. Yeah, this sucks. Wait a second. So now it looks different. Detecting and characterizing the different magnetic textures in a film fewer than a 10 atoms thick required a special scientific tool. Yes, I bet so. Argonne physicist Wu Li led that challenging task using an instrument called a Lorentz transmission electron microscope. The Lorentz force. This microscope includes aberration correction technology to improve its resolution. This TEM can visualize the magnetization of materials at the nanoscale under different magnetic fields over a wide temperature range, a unique capability available at Argonne. The range extends from minus 280 Fahrenheit to room temperature. 20 degrees plus, or what? The team performed additional magnetic and other imaging at Argonne Center for Nanoscale Materials, a dual DOE Office of Science user facility. More basic research is needed to fully understand the behavior of skyrmions and mirrors under different conditions and how to employ them in coding information, Balikas said. Many seemingly science fiction schemes are out there. Many seemingly science fiction schemes are out there. We cannot predict the future, but it seems likely that one or more might come to fruition. I've been talking about this magnetic vortex thing. The surface conductivity anomaly in Scandinavia and how it might affect the weather pattern more and more and more since Earth's magnetic field gets weakened and these conductivity imprints in the crust of Earth. They might get a much bigger role in the future. And maybe I have this even seen already with my own eyes. Back in August, when there was a surprise geomagnetic storm. This event was not in the forecast, so the resulting auroras came as a surprise. And they happened here. At the interface of the polarities of the surface conductivity anomaly. And even the direction of the auroras, they are quite fitting with the interface. Yes. It's really scalable, the electric universe, from the smallest to the biggest. And it's very amazing. Let me show you just still one thing quickly. Since talking about weather patterns and stuff like that, I really wanted to show you this Kongpop Uyen part of the video. Takes probably a few minutes, but check this out if you haven't seen that. Sorry for interrupting, but I just want to show you that this would be planets. And in the first, like in the really at the beginning, they were aligned, and now they aren't. So watch the pattern, how it's changing. Yeah, let's just have a listen and watch.
So just keep moving. Now we're gonna misalign everything. So now we move Venus out of the orbit. It still have some symmetry in it. Now we're gonna move everything out. So all the energy is scattered. So now everything's all over the place. As you can see, if you assume Earth is the third planet here, um, what happened on the outer planet does not have much influence on the energy of the inner ones. So that's when planets are aligned, four of them. That's three. And of course, it just moving out, see like the fourth planet doesn't really have a lot of impact. So next, when it's aligned and not aligned at all. So we can start to see how so many people have been using planets to do the prediction. And I believe this is the reason, because during that time, there's a lot of things that fluctuate more frequent than other times. So next, we look into more evidence of this resonance. So we look into the harmonic resonance of the solar system. We should be able to see such harmonics occur on the planet level. And the best place to look at it is at the pole area. And at the pole, you can see dualities. There's a black spot on the North Pole of Mercury. There's a white spot on the South Pole, so that there's a temperature difference. So in Venus, so that's one. The second planet, you got two vortices. One in the North Pole, two in North Poles, and two on the South, which have like an infinite shape. And of course, on Earth, it's very hard to see, so we looked at the wind system. On the South Pole and North Pole, you look at the wind map, there are kind of roughly three vertices occur. And it's actually coincide with one of the research by Bruce Levon, who have proposed how the energy coupling from space for the Earth as a Y and delta transformer, which consists of three nodes. And of course, if you look at this, if you guess what happened on Mars, you should see four vertices around the pole, and that's, you see about like rectangular shape. And on the South Pole, now all the ice kind of start to vanish. You see there's less ice on the center. And the Jupiter, we're not quite sure. But of course, it's a popular one, which is the Saturn. We've got six, the hexagonal shape at the pole.
Yes, so much about scalability. Thank you. Bye.